Well, it's a pleasure to introduce our next speaker, Claudia de Rham from Case Western, on dark energy and modified gravity.
Thank you. Can you hear me? No. Is that better now? A little bit? Okay. Well, it's a pleasure to be here, be back in Cambridge, and thank you very much for the invitation to speak. So now that you're all locked in the room, I'm actually not going to talk too much about dark energy and modified gravity, but really about my own models of modified gravity. And I don't... and I'm also going to show you some pictures of my baby, etc. Okay, so we heard how to test gravity, and actually gravity is just doing amazingly well. In all the scales we can think of probing it, it's just passing with flying colors. So you might wonder why you really want to modify gravity. Well, one thing is, if you say that gravity is doing amazingly well, it's good to have a comparison. It's good to see another theory which is not doing amazingly well, maybe, or have an alternative, and that's what I will provide. But mainly I will provide some theoretical motivations for this alternative. And of course, they're not coming out of the blue. They're mainly coming from the consideration of observations of late-time the universe, particularly the late-time acceleration of the universe, and actually mainly the cosmological constant problem. And I will take the approach of whether it could be that this observation, or the cosmological constant problem, actually comes from the first time of the breaking down of the theory of general relativity on large distance scales. That's why I'm going to specify theories of modified gravity in infrared, and specifically massive gravity, but not uniquely. So when it comes to the cosmological constant problem, or dark energy versus the cosmological constant problem, I'm going to remain a little bit agnostic and leave Cliff be the Napoleon here. And I'll show you that whether you want to take dark energy or cosmological constant or anything in between or anything else, well, modified gravity and specifically massive gravity is the guy for you. So just stick with me. If you really want to have the acceleration of the universe being sourced by some kind of dark energy, new degrees of freedom, you can think of these degrees of freedom as just arising from the matter sector, and that's just fine. And they can have their own natural realization or not. But you can also think of them as coming from the dark sector of gravity. And there are some models like DGP, which is maybe observational roll out now, but there are models of massive gravity of FFR. And in some of these models, it's not clear whether the degrees of freedom are really intrinsically from the gravitational sector or more from a matter sector, just gravity with some extra scalar fields. But theories of modified gravity, specifically these two theories here, come in hand with degrees of freedom which actually want to accelerate the universe by themselves. So already in the dark energy sector, you can see that modified gravity could have some implications. Now, if you really want to take the cosmological constant as your source for the acceleration of the universe, this is great, but you're also faced with the all cosmological constant problem, which is why is the amount of energy density we see as accelerating the universe is 120 orders of magnitude smaller than the Planck scale. And I should say it's not really fair to say that this is just a problem with a cosmological constant. In most of the time when we put some extra degrees of freedom in the dark energy sector to accelerate the universe, we make such a tuning as well. For instance, if we want quintessence scalar field, the mass of this field will typically be of this order of magnitude, not to give too much back reaction. And that's the case as well in massive gravity, for instance, that the mass of the graviton that we would want to accelerate the universe, if we wanted to accelerate the universe, would need to be 120 orders of magnitude smaller than the Planck scale. In the case of massive gravity, it is a tuning, but it is a technically natural tuning in the sense that if you consider another particle, massive particle, and you look at the loop from this particle, the effects it has on the running of the graviton mass, it will be proportional to the graviton mass itself in such a way that it is a stable tuning to set the graviton mass to be small. And this is actually not something that we expect. It's something that we have now proven with a few other people in specific theories of massive gravity. And then this is different from, for instance, setting the vacuum energy to 0, because we expect, or we can compute, the contribution from massive particle at one loop or any loop to the vacuum energy, and we see that they contribute with the mass of this particle to the 4, so it's not a stable tuning to set the vacuum energy to 0. And that's why even though there's a tuning in both cases, in cases of massive gravity, this tuning might be a technically natural tuning, or technically stable tuning as opposed to technically unstable tuning. And the main motivation, I started working on massive gravity, and I'm not going to talk too much about that today, but that was one of the main motivations, something we still have in the back of our mind, is that in massive gravity or in theories of modified gravity in the infrared, you might have the opportunity to be able to have the vacuum energy as large as you would want it to be, and have its effect being small, or have its back reaction on the geometry to be small due to the modification of gravity in the infrared. So this is something which hasn't been fully worked out. I don't know right now if there's ever going to be a solution within this direction, but that was one of the motivations behind it. And this is the idea behind degravitation, where we're filtering out the effect of a cosmological constant. So that's the motivation for modifying gravity. Now we know that gravity is a beautiful theory, and theoretically it's extremely well motivated, and it's extremely difficult to modify it. As Lam was mentioning before, there's actually some theorems that tell you that gravity is the unique theory of a massless spin-2 field. So in order to modify gravity as little as possible, or to still remain theoretically in a viable theory, let me start with 5D theory of general relativity, and then let me see how I can get different theories in four-dimensional gravity, which will be theories of modified gravity, but the symmetry is present in 5D gravity, and the amount of degrees of freedom that you have in 5D gravity will allow you to ensure that your four-dimensional setup you get out of it is theoretically viable. The first one I will start with is Galileon's. This is not a theory of modified gravity, but it's a theory of 4D gravity with some scalar degrees of freedom there, which have some specific consequences. And in particular, they come in with their own special screening mechanism that Lam talked about. In this case, it's a Weinstein mechanism. And then I will briefly mention the DGP model as arising from 5D gravity, but not really talk too much about it. And I will focus on theories of hard mass gravity and see how they can arise from 5D gravity, and see how actually they look in some limit as Galilean theories, and how the Weinstein mechanism inherited from Galilean theory applies to massive gravity, and see some consequences, mainly theoretical, of that. So let me start with 5D gravity. And not only actually 5D gravity, but something else that I can add in 5D is some Lovelock invariance. In 5D, I also have a Gauss-Bonnet term, which is non-trivial. And if I don't really want to live, I know we're not living in 5D, so let me stick a brane within this 5D and say that we're going to be living on this brane. The brane is localized at some position pi of x. This is going to be the brane bending mode. And if I add a brane bending mode, if I have a brane, I also can induce on that brane a cosmological constant or some four-dimensional scalar curvature. And then on that brane, from the five-dimensional curvature and the Gauss-Bonnet terms, I'm going to have the Hawking-Gibbons boundary terms, which will lead me to actually four different operators of this brane bending mode pi living on the brane. And in the non-relativistic limit of the brane motion, or really it's more a weak field limit, I obtain actually the four Galilean invariants which were proposed by Nicola Sbartazzi and Cincirini in 2008. This is in a non-relativistic limit. I think most of you are familiar with this one. If I had a cosmological attention on the brane and I did not take the non-relativistic limit, I would have the dBi action on the brane. These are the dBi generalization to this kind of term. And we can see that this leads to the four Galilean interactions. The reason why these Galilean types of interactions have enjoyed quite a lot of success since their proposition in 2008 is because they have quite a few interesting properties. They're not just random interactions that people wrote down. First of all, they have some specific symmetry, which is realized after integration by parts. So it's a symmetry of the equation of motion. It's not a proper symmetry of the Lagrangian. It's a symmetry of the action if you have the right boundary terms, if you want. And because of that, actually, these terms satisfies a non-renormalization theorem, because due to the symmetry, you would expect that any operator that you're going to get from configurations of loop is going to respect the symmetry as well, but directly at the level of the Lagrangian. And since these operators did not satisfy at the level of the Lagrangian, you're not going to renormalize this operator per se. You're going to renormalize some other types of operators. And this is also tied to the fact that you can consider this finite number of operators as being large without going beyond the regime of validity of your effective field theory, because anything else which would be generated is going to come in with higher derivatives, and therefore you can work in a regime where they are suppressed compared to these operators. And this is crucial for the Weinstein mechanism to work, because the Weinstein mechanism was going to rely on this operator being large, yet being able to trust your theory within that regime. And even though they have higher derivatives, they've been constructed in such a way such that they have no ghost. In the way they were realized from a 5-dimensional Lovelock variant setup, this is kind of obvious. We didn't have any ghost in the 5D theory, and we don't inherit any ghost in the 4-dimensional counterpart. One of the reasons why these Galileo interactions are interesting is because they can create their own condensate and lead to the acceleration in the universe. So the first two here that you can barely see, they can compensate each other, and that's what led to the self-accelerating solution in the DGP model. This was unstable, it had a ghost. Now if you consider the other interactions which are hidden there, you can actually have some self-accelerating solution, so acceleration through this scalar field without any ghost, the ghost which was there in the DGP model. And yet, as Lam mentioned earlier, so even though they can play a role on cosmological scales, they are hidden on smaller distance scales via the Weinstein mechanism. So what is the Weinstein mechanism? Let's think of the gravitational force between the Earth and the Moon in this theory. So we have the standard gravitational force, and here is, in a Galilean theory, it's not a helicity-zero mode, it's just its own scalar field in its own right. This is actually inherited from a massive gravity slide. Never mind, that will apply as well. If this was the end of the story, then you would think that the gravitational force between the Earth and the Moon would be larger than just in general relativity, where you just have the one mediated by the standard gravitational force because of this extra term that come in the two. But the Weinstein mechanism works by having all the interactions for this pi field, for this Galilean field, becoming important, and they kind of freeze the fluctuations of the field itself on top of it. So they kind of play the role of a honey, on top of which the fluctuations of the field itself becomes weakly coupled to anything else. So it's strongly coupled to itself, which makes it weakly coupled to the rest, to anything else, and even to its own self-interactions. And this can happen only if the interactions for this Galilean field happen at an energy scale which is much smaller than the Planck scale. Otherwise, you would never need to include these interactions before you are reaching the Schwarzschild radius, for instance. So to see that a little bit more precisely for a Galilean model, let me not worry too much about what kind of interactions we have here. It could be the third Galilean or anything else. The thing is, if you have a large source, you have a large source in your theory, for instance, you have the Earth here, close to that source, the interactions will dominate over the usual kinetic term, over the free theory here. So if I perturb my field around a large background and then fluctuations, the large background, which will be determined by the main source, is going to dominate, and is going to redress the effective kinetic term for your fluctuations, so that you actually need to canonically normalize your field. And when you do that, the effective fluctuation sees a coupling to external matter which is suppressed by this renormalization, and is actually quite large. So that makes the effective coupling to matter being extremely small, or the scale being much larger than the Planck scale, due to the external background field from the external matter present here. So this is the essence of the Weinstein mechanism said roughly, and that applies in a theory of massive gravity. So now let me construct different theories of modified gravity. Starting again from 5D gravity, we see that we have the Galileans, and the DGP is actually, in some limit, looks like a special case of the Galilean, where you just have the cubic interaction. Or you can have a theory of hard mass gravity also arising from 5D gravity, which leads to a Galilean in some specific limit of the theory. So if you want to start with 5D gravity, but yeah, we observe only 4-dimensional gravity here, you need to find a way to localize gravity or to confine it or do something about it. So one way, as I mentioned before, is add a brane. And that's not enough to localize gravity. You really need to put some curvature on the brane. So this is the DGP model where you have an interplay between the 5-dimensional part of your gravitational field and the 4-dimensional part. You have two Planck scales, the 5-dimensional one and the 4-dimensional one. Period is both independent. More realistically, you expect them to be of the same order of magnitude, but in the case of the DGP model, you actually take the 4-dimensional Planck scale be much larger than the 5-dimensional Planck scale. In such a way that you obtain a scale out of your theory which is like this, and this scale can be actually very, very small if you take the 4-dimensional Planck scale to be small. Out of this theory, from a 4-dimensional point of view, you get a spectral representation for your graviton, which looks like this, with a character scale which is here, and that corresponds to a theory of soft massive gravity. It's not like you have one single graviton, massless graviton, and then a sum of other massive graviton. You kind of have a resonance, and that's why we call a theory of soft massive gravity. An alternative to sticking gravity on a brane so as to localize gravity and recover 4-dimensional gravity, we can do something which is more common, and we can just think of a small extra dimension. So I should say in the DGP model, we can have an infinite extra dimension. The mechanism still works. If you want to avoid an infinite extra dimension, what people have been thinking more in the past is just to have a small extra dimension. Here I just compactified it, but it doesn't necessarily need to be the case. You can think of all the boundary conditions. It just needs to be a finite size. And here we usually thinking of doing a Kaluza-Klein decomposition. I'm not going to do a Kaluza-Klein decomposition. I'm going to actually do a deconstruction, a discretization of the extra dimension. But at the end of the day, the two things are completely equivalent after a fieldwide definition. And this is something which wasn't obvious necessarily in the beginning. Either for a Kaluza-Klein decomposition or for a deconstruction, what you'll get for the spectral representation is a superposition of massive modes, a massless mode, and then some massive mode with the mass difference being related to the size of the extra dimension. And then if you decide to discretize your extra dimension with n points, then the most massive mode would be n over r. So that's where your truncation stops. In both cases, for DGP, whether you want to stick gravity on a brane or whether you want to have a hard theory of massive gravity. So this is a hard theory of massive gravity because you really have separate massive gravitons. You end up knowing that you start from a 5-dimensional theory of gravity, which only had for a massless theory of a massless spin-2 field in 5 dimensions having 5 degrees of freedom. Starting from that theory kind of ensures, if you know what you're doing, that you only end up with 5 degrees of freedom from your 4-dimensional point of view, and so 5 degrees of freedom for your massive spin-2 field in 4 dimensions, which is the right degrees of freedom to avoid the normal ball-wide ghost instability. So this is kind of a mechanism that allows you to make sure you're not doing anything wrong. There's some, you really need to do, it's easy for me to say now that I know the answer, that how to get it. People have tried that 10 years ago, doing a deconstruction to get a theory of massive gravity, and they were obtaining a ghost due to some other reasons. But I'll show what it is you have to do to avoid this ghost-like instability. In both cases, as I mentioned before, be it DGP or being hard mass gravity, you end up in some limit with a theory of gravity with a scalar degree of freedom, which looks like a Galilean scalar field. I should say, it's not because in some limit it looks like gravity with a scalar field that it is just a theory of gravity with a scalar field. In massive gravity, the gravity part is really different. The graviton really does have a mass, and that will mean that the gravitational force will have a finite range. It's not just a theory of GR plus a scalar field. You do modify your theory of gravity. And because they behave as we can see that they have a Weinstein mechanism as they look like a Galilean, the scalar part or the helicity zero mode of the graviton behaves as a Galilean scalar degree of freedom in some limit. And that's the easiest way to see how the Weinstein mechanism gets implemented in this case. So let me go a little bit through the deconstruction of 5D gravity to obtain a theory of 4D massive gravity, because it's something which wasn't completely obvious from the beginning and actually led to a few misconceptions. So this idea is not new. It's 10 years old, and actually it's much older than that. People try to do that for gauge theories, etc. It didn't work originally. If you start with your theory of 5D gravity and you start to discretize, people were recovering the Ball-Ward-Desser ghost, but actually it's being pointed out by these very nice papers here that really in such theories, the fundamental objects you should work with is the field-bound field. And most of the time, it doesn't really matter whether you want to work with the metric or whether you want to work with the field-bound. But if you want ultimately to couple your theory with fermions, then the field-bounds are the guys. So it's always better to start with the field-bound. If you can go back to a metric language afterwards, that's OK. If you can, then that's too bad. So let me start with the field-bound, and we'll discretize the field-bound. So starting from a continuous theory, what I can do is at every point, instead of saying that they are a function of y, I just say they are the nth part of my field, and I'll do that for the field-bound. This is all fine. If we start with a theory of 5D general relativity, then we're going to have y derivatives along the extra dimension. So I need to define what I mean by that. So this is the extrinsic curvature, which corresponds to the derivative of the metric, which I want to write as a derivative of the field-bound. And that's where my discretization procedure comes in. Instead of having a e at a given y, I split them into en. And instead of having a y derivative, a derivative along the extra dimension, I substitute this by its discrete counterpart. So that's what gives you the relation between what's going on at one place, at one site, with what's going on at the next site. I decide to write the derivative like this. You can have a 2 or 3 sites derivative. That really doesn't change anything at all. And also, at this level, I decide to define what the field-bound is as being what it is I want. But I could decide to be the average between 2 points or something different. That's actually interesting. They're going to generalize the theory of massive gravity. But at this level, it doesn't change at all. So all you need to do is this really basic discretization procedure. That's really nothing difficult at all. You plug that back in. And so what you get for your extrinsic curvature, so for the derivative of the metric along the extra dimension, is some difference between field-bounds, which written back in terms of the metric, you obtain a square root structure which corresponds to the interplay between the metric at one point and the metric at another point. And for those of you who've seen a little bit of massive gravity before, you recognize the square root structure that you need to have in massive gravity to avoid the Ball-Ward-Desser ghost. But from here, that's just inherited automatically from the 5D from the direction. So now to construct your theory of massive gravity, it's really simple. You have your extrinsic curvature k, and you replace it by another k, and you're done. So that's your theory of massive gravity in 4 dimensions. Actually, it's not really a theory of massive gravity. In this case, all the metrics at every site is dynamical. So you have a theory of n interacting gravitons. One of them is massless, and the other one are massive. To see the mass spectrum, you would need to do a Fourier decomposition of that. And that's where that corresponds exactly to what you would have had in a Kaluza-Klein decomposition after you do your Fourier transform and a few field redefinition. So this is just to motivate how you obtain a theory of 4D massive gravity out of a theory of 5D massive gravity. You can also do a decoupling limit of that. You're not necessarily required to think of the dynamics at every point. You can just look at the interplay between them and freeze some of the kinetics, and then you will obtain some theory of massive graviton without multiple gravitons. What you can see then, and what you know already from a theory of massive gravity, is that, well, first of all, you can truncate the theory here. You just consider n sites. So you have the most massive mode is at n over r. That's the mass of your most massive mode. And you just truncated your theory there. And there's absolutely no ghost. So it is a completely consistent truncation of your 5-dimensional theory. That's completely consistent with no ghost. What you do have, on the other hand, is a strong coupling scale, which is related to the mass of the lowest Kaluza-Klein mode, or the lowest mode in your discretization. And so that tells you that your theory is strongly coupled at that scale. And then when you try to send m to 0, or the size of the extra dimension to infinity, you don't recover 5-dimensional gravity because your theory becomes stronger and strongly coupled. The Weinstein mechanism works more and more. You're freezing your 3 extra degrees of freedom that you have per sites, and actually you don't recover your 5D continuous theory of 5D gravity with 5 degrees of freedom continuously. You really recover multiple theories of gravity which are just not interacting. And this is what you wanted to have in the first place. So there's kind of a trade-off of whether you want to be able to have a truncated theory of interacting gravitons from a four-dimensional point of view, where you want to be able to trust your theory all the way up to that scale there, in which case you need to do the discretization in the way I've set it up, where actually you need to set some gauge before you do your discretization, and the gauge we set here is setting the 5-dimensional lapse to 1. Or you don't do that. If you don't do that, then the game is completely different. You don't obtain this strong coupling scale, but also you obtain some degrees of freedom which are there related to the lapse degree of freedom, which tells you that you cannot truncate the theory at that scale because you keep a ghost at that scale. And that ghost only disappears when you send this scale to infinity, when you recover the continuous limit. So either you want to be able to have a truncated theory, and then you will get you really will get your truncated theory with a strong coupling scale, and you're not going to recover 5-dimensional gravity, or you do your discretization in such a way that you never going to look at a truncated theory and you'll be able to recover your 5D theory. Okay, so let me go a little bit quicker through the next point and just tell you how this theory is actually stable to some extent from a quantum point of view. The absence of ball-wide as a ghost, the absence of 6 degrees of freedom, is tightly related to this specific structure of the potential. And one way to see how this is a nice structure is once you get, you should see the Galilean appearing as the helicity zero mode, which appears after Schuckerbergization. If you don't know this word, just have a look at the Oxford Dictionary of English Language, and that means G mu goes to this thing. Yeah, you might be used to this. This is what you do, and that's what Schuckerberg did when he wanted to include this for the photon, for the Proctor field. Now, being GR, you have to do some nonlinearities. You need to include this thing here. And because it is quadratic here, this is related to the fact that you need to have a square root come in here. This special structure removes all the high derivative terms in pi. And what you obtain is a Galilean for the field pi in here. Now, this special structure, you expect it to be destabilized by quantum corrections. If I look at just a one loop to the two-point function, it won't preserve the nice Fierz-Pauli structure that you have here. And that will tell you that you would expect to recover a ghost by quantum corrections. If you just look at that diagram, that will come in at the Planck scale. So from here, you just expect the mass of the ghost to be the Planck scale. That's not something you should worry too much about. But if I think of a higher endpoint function, then I will have something which looks like this. And if I put myself on a big background, then this n operator, this higher operator, can look like a ghost with some of these arising from the background structure. And now we see that the Weinstein mechanism relies on this thing being extremely large. So that will tell you that this is small. So if you are on top of a large background configuration for your field, you expect by quantum corrections to generate something which would lead to a mass of the ghost which should be much smaller than the Planck scale. And actually, this you can find easily backgrounds for which this will be smaller than the scale lambda. And so you recover the ghost within the regime where you would like to trust your theory. And so you just rolled out. Well, that's not the end of the story. Actually, the way this happens, if you're thinking of large configurations for your field, you need to do that not only at that level, but you need to see how that redresses also the two-point function and it redresses the whole one-loop effective action. So if you do it consistently at the level of a one-loop effective action, this is something we've done with Raquel Ribeiro, who's maybe here somewhere, and Lavinia Heisenberg, you see that not only it redresses what you expect here, your mass matrix, it also redresses your whole propagator in such a way that when you're considering large configuration for your background, this thing never becomes much larger than 1. And so even if you're on top of large background configuration, the mass of the ghost is never going to become smaller than the Planck scale, even if you're on top of that. and that seems to work out nicely. So it's really telling you how the Weinstein mechanism is also working at the quantum level. This is at the level of the one loop effective action, but we expect the same thing to happen even better at higher loops. So now let me finish in the last 10 minutes by some potential issues that arise in Galilean models, and this is going to happen typically in theories of massive gravity as well, and happens in DGP as well. So let me go back to the simplest Galilean model, which is just the cubic Galilean, just because it's simpler, but the same thing happens for all the Galileans. And once again, let me split this field into a background configuration, which I'm going to consider to be large. So this thing is large, and some fluctuation, which are called pi again. And what happens is that redresses the kinetic terms like this, and that affects the theory in two potentially very bad ways. First of all, we see that the effective metric that the fluctuation sees has changed. So it has changed the kinetic structure, and that tells you that it might potentially change the causal structure of your field. So if you have two different fields, the standard model fields and the Galilean field, which sees two different effective metric, then you can have some which don't have the same causal structure, then one field can propagate superluminally with respect to the other one. And that has been pointed out in the case of massive gravity by Dazer and Waldron this year. And based on this result, people have then used the causality, went back in time, and wrote some papers since this year there showing that the same thing happened in a Galilean theory. So this is definitely some trouble that happened in a theory of massive gravity and a Galilean theory in general. Now, something else which is tightly related to the Weinstein mechanism per se is the strong coupling, which is needed for the Weinstein mechanism to happen, but also once you hit the scale lambda, you wonder whether you can trust the theory at all or not. So on top of a background configuration, you have to redress your field. You canonically normalize it, as I did before. And so the redress scale at which the interactions occur is not the lambda, but lambda over square root z. And in the case of the Earth, so if I take, here I'm thinking of a massive gravity theory. So if I take the mass of the graviton to be of the Hubble parameter size, and I take the mass to be that of the Earth, and I'm putting myself at the surface of the Earth, this redress scale is typically of the order of the centimeter. Once you hit that scale, then all hell breaks loose. You don't know what's going on. You don't know if you can trust your theory. So that's actually a very low energy scale to already be hit by quantum corrections. So what do you do after that? Do you just throw away the theory, or do you try to resum these loops in such a way that you can go beyond that? And actually, this is what you can do. And you use the duality Galilean mentioned by Andrew yesterday. So for those of you who were at Andrew's talk yesterday, you might know what I'm talking about. For those of you who don't, then just use the superluminalities, go back in time and see his talk. So both the strong coupling issues and the superluminalities plague a priori a Galilean theory and to some extent massive gravity. There's just a question mark here, not for the strong coupling, but for the superluminalities. It's been shown that some solution of massive gravity have superluminalities. It's not clear to which extent stable solutions of massive gravity, which are consistent, have superluminalities, but that's just a small effect. But actually, it's been shown, and Andrew mentioned that in his talk yesterday, that Galilean theories can be shown to be dual, and in some cases, the dual theory is a completely free theory. A completely free theory, which by definition has no strong coupling issues, it's just free, and has no superluminalities. It doesn't have any interactions, it doesn't have anything. So how could that be? Let me show how that duality works, not in the case Andrew mentioned yesterday, but in a slightly different setup, but because there's different ways you can think of this duality. And for more precision, I really encourage you to look at these talks, because I only have about 1.5 minutes to talk about that, and it's a little bit technical. Let me consider a static configuration for a Galilean, just because it's simpler, and I'll focus again on the cubic Galilean. With this cubic Galilean, I can do a very non-trivial, and it's not non-local. I wouldn't say it's local, but it's not non-local in the usual sense. A field redefinition where I change not only my field, but also change my coordinates. This is something very non-trivial, And that doesn't arise out of the blue. It's actually been shown by these people to be a Lejeune transform. And it's actually what comes in a theory by gravity. That's one of the ways you can see that there's a duality between these two fields. Anyways, you do this field, a coordinate transformation, and what you get out of it, well, it's a cubic Galilean. So you might not have one much. Actually, you do. You do have one a lot, because the relation between the coordinates here and the relation between the coordinates there, and also the relation between, if I had put a scale here, G, what I would have obtained in this case is the inverse G here. You can't see quite it here because I rescale things, but actually when you are dominated by that interaction in the original theory, that corresponds to be dominated by this interaction in that theory. So there's a strong weak coupling duality in this duality. One very easy way to see that here is that the coordinate gets transformed like this. So if you're in a very strong, strong coupling region in the original theory, x is very small, that corresponds to go at x is infinity for the dual theory, where the theory is very weakly coupled. You expect to recover your standard free theory, as I mentioned here. So there's a duality between when these interactions dominate in the original theory and when that interaction dominates in the dual theory, and that's your strong weak coupling theory. So that allows you actually to resum when the theory is strongly coupled here and you have an infinite number of loops to resum in here, that allows you, this field of coordination, to repackage them, and you know exactly what you end up here with your dual theory. So in particular, if you start with your dual theory, you know that your theory will be in the weak coupling region, in the region where this term dominates. Your theory will be under control so long as you don't consider distances larger than the scale lambda minus 1. But now if you read that back in terms, so you do all your calculation in there, you do all your observables in this regime, and now you repackage that back into your original theory. What dx is in terms of the original dx tilde is that multiplied by an extra factor here, which depends on how you were sourced in the first place. You put all of that together. What that corresponds to for your final theory is that what you had done here is in control. So you are within the regime of control of your validity of your dual theory if you're looking at distances which are larger than 10 to the minus 8 centimeters if you put everything, thank you, for the Earth. So that shows you how you have actually, by doing computation in a dual theory, which resums everything out for you, you can go much beyond the scale lambda, which you have originally thought that was the end for your theory. So that's what allows you to go much beyond your strong coupling scale lambda. So let me just finish by saying that, well, we have an exciting theory that allows you to do lots of things, in particular, maybe potentially time acceleration, and maybe sometime we could say something about the cosmological constant problem. We know how to construct a theory of massive gravity, and we actually know how it arises from a theory of 5D gravity. It's actually just a deconstruction, which is completely equivalent to a Kaluza-Klein decomposition. I should also mention that originally people thought that if you started by 5D gravity and you did a Kaluza-Klein decomposition, you wouldn't get any of these strong coupling issues. You wouldn't get these kind of theories of massive gravity. Everything would be sorted out for yourself, but no one really worked that out in detail. And when you do this for a Kaluza-Klein decomposition and you fix the lapse, what you obtain is exactly this theory of ghost-free massive gravity with all the non-coupling, the strong coupling issues that we end up with. It behaves as a Galilean theory, which, in some limit, which potentially has superlunities and strong coupling issues, but they are potentially resolved by the dual Galilean. And the superliminalities I haven't gone through in too much detail, but I'm happy to answer questions about that. And also to see how crazy we are on the Napoleon scale. I'll just finish with that. Thank you.
Well, thank you, Claudia. Other questions?
Thank you for your talk. I have just a comment about one of your first slides. And I'm saying it because it started confusing some youngsters and some people in the field. You put dark energy, and then underneath it you put modification to gravity, and you put if we can look. Yes, so you put new degrees of freedom in the matter sector and new degrees of freedom in the gravity sector. So I think this is creating some confusion because I think the way we have been doing this is that we have cosmic acceleration, and then from cosmic acceleration, that you can have, under that one you have new degrees of freedom in the matter sector and new degrees of freedom in the gravity sector. In which case dark energy is not the englobing idea, but it's rather one of the items. In fact, in your it should go under.
How about I write it dark and then dark energy and dark gravity? Would you be happier?
Yeah, but I think normally to follow the hierarchy, it starts confusing some people about what dark energy is and cosmic acceleration.
But it's good. It's confusing because sometimes it's not one or the other. It's in between, or you can choose. For feather R, it's not really that it is a modification of gravity. It's really a new degree of freedom. So sometimes you might have thought it was a modification of gravity, but really it was just dark energy. So I completely appreciate and understand what you mean.
It's okay. We can debate that later. Next.
So the idea that the Galileans might be UV complete, I think, is super exciting. But I wanted to ask how sure you are that that also applies for massive gravity, because I'm worried about the couplings to matter and whether problems come in when you couple the theory to matter.
Oh, so the coupling to matter is the same for Galilean and almost the same for massive gravity. You have this formal coupling in massive gravity, but that you would know through the duality how to go from one to the other. So it's not that it's going to work for Galilean and it's going to not work for massive gravity. If anything, you would expect it to work better for massive gravity because that's where it arises from in the first place. So this duality arose from a theory by gravity, where you can couple to matter as well, and you can introduce the sugar bulk in one language or another language, and they are completely equivalent because it was your choice to decide who was the real reference metric. So the duality is not going to be broken by adding a coupling to matter in massive gravity, but
Okay.
it's going to tell you how you have to include it.
So the reason that I'm worried is I think if I have the disformal coupling, I can compute a one-loop correction to 2-to-2 particle scattering that is divergent in the UV, and I don't see how.
Yeah, so I think that probably the disformal coupling is what you have in some limit, but in massive gravity, it's not like it's just that. You got it from putting some stuff in your H mu. And so just don't do that in the first place if you want. And that's really the original way you introduce your Stuckable fields and your original way you should see the duality. Only after that you do your field redefinition. So, I don't know exactly how that will work out once you do your diagonalization. But the natural realization is when you're not diagonalized, when you're not diagonalized with between the helicities error. So I don't think this is going to change the structure. In any ways, you know that the coupling to matter is when I haven't written a theory by gravity here, but your coupling to matter is either respect to one metric or to the other, and you do it like that. And one thing I should say though, that reminds me. Thank you. Let me just take this opportunity to say something else. We know actually there's also always the question of why when you couple to matter, you only couple to one specific metric rather than two metrics at the same time or something like that. Here it's going to actually start with your 5D theory of gravity and you add whatever coupling you have. At one given point, you also have one given whatever scalar field chi n, and that chi n coupled to that metric g mu n in a specific way, in a covariant way, if it were covariant. Then you can have some interactions between the species at this site and the species at that other site, which are very like these kind of interactions, but you don't have that the kinetic structure, four-dimensional kinetic structure of the species on that side coupled with another metric, for instance. Yeah. But the duality really arose from, it's your choice to decide in a biogravity theory how you're going to Stucker-Barrize it. And the matter Lagrangian, you don't do the Stucker-Barrization in the matter Lagrangian to start with. Only after diagonalization you start seeing some interactions. Yeah.
I think we should close there for coffee. So let's thank Claudia again.
Thank you.